Hello, welcome to lesson 4 of the topic 4, which is waves and oscillations. So this lesson we're going to cover these topics about wave behavior, phase difference, reflection, superposition, and wavefronts and rays.
Hi, today I have a fun task for you to begin with as a follow-up to our previous lesson. Remember we talked about electromagnetic waves when the electric field vector oscillates in one direction and the magnetic field vector oscillates in the perpendicular direction. So I want you to produce that with your hands. I have never seen anyone do this right before. That's your challenge. If you manage to do it right, send me a video. So when you try it, one hand always goes vertical and like, as you see, I can't really do it. Try it.
Okay, let's get started.
Our lesson today is going to start with a little singing exercise. Row, row, row your boat. Maybe not for me. Let's ask an expert to do it.
Hi, Miss McGay. Happy to help. Row, row, row your boat gently down the stream. Row your boat gently down the stream. Merrily, 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 life is but a dream. Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream. Bye.
Thank you, Ms.Caitlin, for this special appearance. Okay, now back to our topic 4. We're going to talk about a concept called phase difference. Is a measure of delay. In the song you just listened to, there were two singers which sang the same song but with a delay. Here's another demonstration for you. So when two waves are in phase, that means they have the same frequency and they hit the same point at the same time simultaneously. When two waves are out of phase, that means that's not the case, there's a delay. Just to clarify the measurement in terms of time, let me go back to this point and watch again. So that's half a period out of phase. You can see when one drumstick is at the top, the other drumstick is at the bottom, and vice versa. So they're exactly half a period out of phase. That is a measurement of how delayed one is compared to the other. Next, watch again the quarter phase difference. So phase difference is defined as a measure of the delay between two waves expressed in degrees or radians between two waves having the same frequency and reference to the same point in time. This diagram that we see right here shows two waves that have a phase difference of 90 degrees. Now, phase difference can also be expressed in terms of the wavelength or the time period. For example, the above graph shows two waves with a time delay of t over 4. So when one wave starts at t equals 0, the other wave is a quarter period delayed. So it reaches the same point a quarter period of time after the first one. This is the same delay when we express it in terms of the wavelength, because in quarter period of time, the wave will have traveled quarter of one wavelength. In terms of the angular displacement, this corresponds to quarter of a full 2 pi displacement. A quarter of 2 pi is pi over 2, which obviously is also equal to 90 degrees. So all of these versions are equivalent to each other and they all mean the same thing and they can be used interchangeably. Here's another example to show you a quarter period phase difference. If this is the first wave, think about how the wave which has a quarter period delay compared to this one. If that is what you thought, you are right. Another example, same wave, Now think about how it would look if there was half a period of delay, which would look like this. As you can see, all I did was shift the graph by half a period. Okay, our next discussion is reflection of waves. First, I'm going to show you a demonstration that I recorded at home. This is the setup. As you can see, I have a power source connected to a light box and an angle measuring template at the bottom. And this is what I'm going to use to make my mirror. Now, I had to shoot this in the dark, obviously, to see the ray clearly, but I have made labels for you to see how the mirror is aligned. The perpendicular line drawn to the mirror is called the normal line, and this is the ray that I will be sending to the mirror. Please observe the relationship between the incident ray and the reflected ray. How reflection works is basically shown in this diagram. If this is the mirror, the perpendicular line to the mirror at the point of incidence is called the normal line, incident ray, and the reflected ray. The rule is that the angles measured between the incident ray and the normal and the reflected ray and the normal are equal, as you saw in the demo that I showed you before. So the incident wave, reflected wave, and the normal line are on the same plane. It's a two-dimensional pattern, and the angle of incidence is equal to the angle of reflection. Now, I know in this particular case, it doesn't matter which angles you're using, because if you measure the angles made with the mirror on each side, obviously those will also be equal. But that's only in this case. Get yourself used to measuring always the angles between the ray and the normal line. This is not a special angle. This is not the angle of incidence. The angle of incidence is always between the incident ray and the normal line, and the angle of reflection is always the angle between the reflected ray and the normal line. This will be crucial in our future lessons when we talk about refraction, when they won't be equal. Okay, moving on. There are two cases of reflection we can talk about. We can talk about reflection from a fixed end or reflection from a free end. Again, to demonstrate, I have made some videos for you. So how did the pulse reflect from the fixed end? I'm sending the pulse from the right side. It reaches the fixed end. Did you see that it comes back from the other side? Here's another example. This is not very accurate, but I wanted to show you anyway. I fixed one end of this decorative beads, which you might have at home. And please try this at home if you have one of these nice decoration beads, which is actually why I put this here in this video, to show you what you can do to observe this yourself. So let's watch. See that it comes back from the opposite side. So the pulse actually got inverted when it reflected from the fixed end. Now, to show you reflection from a free end with a real-life example, which again is something you can do if you have any of these decoration beads, hang it from a fixed point. Make sure it's hanging with no movement at all, and make a pulse like I did, and watch how it comes back from the bottom end. There it is going back. And from the fixed end, it's coming back. So what we saw, I sent the pulse from the left end. This is a free end. There's nothing keeping it fixed so it is free to move, so it does, and the reflected wave goes back on the same side as it came from. Well, this is a fixed end, so we see it get reflected as it goes down again. Let's see this again. On its way up and back down. So what just happened? I created a pulse on this end. It went forward, fixed end, came back from the bottom, another fixed end, again got inverted. Every time it reflected from a fixed end, the pulse got inverted. Let's see this in slow motion. And as you do, I want you to watch this particle. So when the wave reaches that point, that last particle, the green one, has nowhere to go. When the energy reaches to this point, even if this particle transfers the energy to that fixed one at the end, the green one cannot oscillate. So where will the energy go? So it continues. It finishes its oscillation and moves down, which pushes this one down and pushes that one down. Keep watching. There it is. So we see the wave inverted. Same thing happens on the opposite end. Because the fixed end particle is unable to move, the particle that carries the energy to the final fixed particle has to complete the oscillation because energy is conserved. This time the particle at the end is free to move, so it will. Fixed end, free end, slow motion. Watch the particle at the end. Can go up, come back down, just the way it came. And this one is a fixed end, so it gets inverted. But from the free end, we don't see any inversion. So let's summarize this. A wave goes through pi phase change when reflecting from a fixed end, which is what we see in this diagram. A wave on a string reflecting from a fixed end. This is the incident wave. The reflected wave will be inverted, which means it goes through half a period of phase change because the phase difference between a crest and a trough basically is half a period. This includes light rays as well. We don't see it in this picture because we don't see the phase in a light diagram. But yes, the wave also behaves as if reflecting from a fixed surface because the water represented here, or glass, is denser than air. We will look more into this when we talk about refraction. When a wave reflects from a free end, the incident wave and the reflected wave will be in phase. So a wave goes through zero phase change when reflecting from a free end. Okay, our next concept is superposition of waves. And let's watch again. This time I'm going to create two waves on this slinky, and they will be from two opposite sides, and see what happens when they meet. Right there, what happened? You can try to do this at home if you have a slinky, or you can try to do it with the decorative beads if you want to give it a try. But what we saw is this. So first I'm going to create a pulse like I did before, but then I'm going to create another one and have them continue. Here goes the second one, and they meet. Whoa, what happened? They met somewhere here. Okay, here's another case. This time I'm reflecting from a free end, And here goes the second one, and they meet and whoop. Destructive and constructive. So here goes the principle of linear superposition. Pulses and waves, unlike particles, pass through each other unaffected. And when they cross, the total displacement is the vector sum of the individual displacement due to each pulse at that point. Basically, when a crest meets a crest, we call that constructive interference. When a crest meets a trough, we call that destructive interference. So the amplitude of first wave plus the amplitude of the second wave adds to twice the amplitude. The amplitude of this wave and the amplitude of that wave, because they're in the opposite directions, they again add up, but they add up as the vector sum. So they add up to 0, which we call destructive interference. Okay. The last concept we are going to learn in this lesson is the concept of wavefronts. This is our way of representing waves in two-dimensional diagrams. So let's watch this first. Here's a wave. Water drops onto the surface of water. And here's a top view. So this image shows the wavefronts. That's the wave we're looking at. And you can see each of the drop point as the start of the next wave. So each of these dark lines can represent where a new drop comes in. So the next dark line would be one wavelength away. So the diagram for this could look like that. These are circular waves from a point source. So the wavefronts look like circular, and the wave is traveling radially outward. The distance between each wavefront is one wavelength. So a ray is an arrow which represents the velocity of propagation of energy, and wavefronts is what we represent each repetitive point on a wave. Here's how it works with plane waves. Here's the three-dimensional image, and here's what the wavefronts would look like. And obviously, since these are plane wavefronts, the ray would be moving forward and the wavefronts are parallel to each other. Again, the distance between each wavefront is one wavelength. What do you observe about the relationship between wavefronts and rays? The answer is they're always perpendicular to each other. Now I'm increasing the frequency. See what happened to the wavefronts? Well, when you increase the frequency, since the speed is constant, we should see a decrease in wavelength. And we do see the wavefronts getting closer to each other, which means the wavelength is smaller at higher frequency, which makes sense. Here's how it works with plane waves. At higher frequency, and again, you see the wavefronts getting closer to each other, even higher frequency. Okay, that's it for this lesson. Here's your homework. See you later.